Hey everyone, let's go ahead and look at another example of sketching the graph of a rational function. So our example this time around is the function f of x equals x cubed minus 1 in the numerator and x squared minus 9 in the denominator. So let's jump right in and do our first step of finding our intercepts. And so like before, we'll save our y-intercepts for later, maybe use that as a test point if needed. Let's go ahead and try to find our x-intercepts, which occur when the numerator is equal to 0. So we have to solve the polynomial equation, x cubed minus 1 is equal to 0. Add 1 and take the cube root of each side, and you find that x is equal to 1. This is a degree 3 polynomial, so it could have up to 3 real solutions. However, there's only going to be one real solution in this case. The other two solutions are going to be complex conjugates that we're not going to need when it comes to graphing. So in the second step of our procedure, we're looking for our asymptotes and our end behavior of our function. Let's start by finding the vertical asymptotes of our function. Remember, the vertical asymptotes occur when we get division by 0, which happens when our denominator is equal to 0. So when is x squared minus 9 equal to 0? We can factor or add and take the square root, but we'll find two solutions here. We have two vertical asymptotes, one at x equals positive 3 and another at x equals negative 3. Okay, so we need to remember that if we want to determine the end behavior of a rational function, it all comes down to comparing the degree of the numerator and the denominator to figure out what the next step is. So if we look at the degree of the numerator here, it's a degree 3 polynomial, and the denominator, we have a degree 2 polynomial. So the numerator is bigger than the denominator, which means we might have some kind of slant or oblique asymptote here. We have to do some polynomial long division to help us determine the end behavior. All right, so let's go ahead and quickly perform our polynomial long division so we can rewrite our rational function in a more useful way to find its end behavior. To get the ball rolling, how many times does x squared go into x cubed? Well, it'll go in exactly x times. If we multiply our divisor by that first term in our quotient, we get x cubed minus 9x. We have to subtract that entire quantity away from the dividend. That gets rid of those x cubes. We have a double negative going on here, so we're left with a positive 9x and a negative 1. And now we're ready to repeat this process. Oh, but we can't because x squared cannot go into 9x an x or power of x number of times. So it stops right here. It terminates. And what this tells us is that we can rewrite our function as x plus 9x minus 1 over x squared minus 9. And the important part here is that that quantity 9x minus 1 over x squared minus 9 is going to vanish when x gets really, really large and positive or really, really large and negative. And all that will be left over is that first term of x. And so that first piece of x is what our function is going to basically turn into for large values of x. But that's just like y equals x. So our end behavior is going to be the slant or oblique asymptote described by y equals x. All right, so before we pick out some test points, let's go ahead and plot the information that we already have found. First, we have our x-intercept at x equals positive 1. Let's go ahead and say that that is right about there. Then we have these vertical asymptotes at x equals positive 3 and negative 3. Remember, we indicate our asymptotes with these dotted or hashed lines. So we also have to have one over here at negative 3. That looks to be right about where negative 3 should be. So here we have our two vertical asymptotes. We already got our x-intercept. Next is the end behavior. The end behavior is also going to be a dashed line. It's asymptotic. It's the line y equals x. Remember, the line y equals x is describing the end behavior, meaning as x gets really, really large, positive or negative, our function is going to approach this slanted line. One thing we have to be a little bit aware of, the difference between, say, a vertical asymptote and a horizontal asymptote or a slant asymptote is our function, the graph, can never cross a vertical asymptote. However, there's nothing stopping a function from crossing a horizontal asymptote or a slant asymptote. So that may occur in our picture here, but we should not be crossing these vertical lines. And that makes a bit sense too, because remember, this slanted line is really describing the behavior way out to the sides, far to the right and far to the left. So we can actually erase this middle piece if we wanted. It's not used to describe local or short-run behavior. All right, so now we are ready to start picking our test points to figure out exactly how our function is going to behave in all these different regions throughout these different intervals. And so we have to pick test points between and beyond each x-intercept and vertical asymptote. And I always like to work from left to right. So our leftmost feature here, besides the slant asymptote, is this vertical asymptote at -3. And so we need a test point to the left of -3. Well, -4 is certainly to the left of -3. And again, I think we could probably get away with avoiding this test point if we carefully use our asymptote here to assist us. But if anything, this will just verify what we can notice from using our asymptote. So if we plug -4 into our function x^3 - 1 over x^2 - 9, the output I get is about -9.3. More importantly, it is a negative output. And that's what we expect, right? Because as we move to the left, we have to approach this line that is also always negative. So -9 should be probably somewhere way down here. That's when x is equal to -4, which let's say is right about there. Just making a quick edit right here. I'm going to move our y value of -9 a bit higher just so it fits on screen and makes our picture look a bit nicer. So we're at the point -4, -9.3. As we move to the left on our graph, we have to approach our slant asymptote. So our function has to very closely get close to and basically become this slanted line. We have to also, as we move to the right, respect and approach this vertical asymptote at x equals -3. We know our function is negative on this interval, so that means we have to go down towards -infinity as we approach x equals -3 from the left-hand side. All right, so that takes care of this far left interval beyond our vertical asymptote at -3. Next, we need another test point between our vertical asymptote at x equals -3 and our x-intercept at +1. And this is where I think the y-intercept makes a great test point. So what is the y-intercept of our function? Well, if we plug in x equals 0, we get 1/9 or about 0.1 repeating. And so that'll be pretty close to the origin, but not on the origin itself. And so that tells us when we are to the left of x equals +1 and to the right of x equals -3, our function has to always be positive. That means we cannot come up from this vertical asymptote at x equals -3 and hit this point, because if we were to do that, we would be forced to cross the x-axis, which means we'd have another x-intercept. But we found all the x-intercepts, all the real ones at least. There was only one. So that is impossible. That means we have to come down from +infinity at our vertical asymptote. Or another way to say that is as we approach x equals -3 from the right-hand side, our function has to increase without bound and go towards +infinity. And so what we also know is that we have to continue moving to the right until we hit this x-intercept at x equals +1. And now our next interval of interest is what is happening to our function between x equals 1 and x equals 3. Well, how are we going to figure that out? That's right, we're going to use a test point to help us figure that out. We just need some nice x value to plug in between 1 and 3, and 2 I think is the best choice there. So if we take the time to plug x equals 2 into our function, the output we get is 7 over -5, or about -1.4. So when x is equal to 2, we're at -1.4. That's probably going to be just somewhere right below the x-axis here. The important piece of information that tells us is that we have to go below the x-axis after passing through our x-intercept at x equals 1. And don't forget, we still have this vertical asymptote we have to approach as we continue moving to the right. It's going to be impossible to turn around and go up as we approach this vertical asymptote, because that would introduce another x-intercept, which we know does not exist. So that forces us to go down as we approach the vertical asymptote at x equals 3 from the left-hand side. So now there's just one last little piece of our graph that we need to figure out here, and that's how our graph behaves to the right of x equals 3. Again, I think we could avoid a test point here because, well, we have to approach this slanted line as we move to the right. And so that means our outputs are going to have to be positive once we're far enough to the right. They couldn't start down here and become positive because, again, that would introduce another x-intercept. So that means they have to come down from +infinity as we leave that vertical asymptote at x equals 3, turn around at some point. We won't be able to find these kind of turning points or these local maximums and minimums until we get to calculus. We do know they have to be there through our analysis here. So it's going to turn around at some point, don't know where, and then approach our slant asymptote. And I bet that our test point will just verify this for us. So what test point should we use to the right of x equals 3? I hope you all said 4, because that's what I'm using. And if we plug in x equals 4, we get an output of 9, which matches up with our picture up here, and actually relatively to scale as well. And so we finally completed the sketch of our rational function here. Remember, the rational function is the graph in green. The pink lines are just our asymptotes. They are not part of our function, but they're helpful to include to help us describe certain aspects and behaviors of our rational function.